So, Chapter 13 deals with a concept called equilibrium. And this is a fairly pervasive concept in chemistry, the concept of reactions being at equilibrium. We're going to be looking mostly at chemical equilibrium for the next couple chapters. And to start with, we need to get an idea as to what equilibrium actually is. So, to start with, when we talk about equilibrium, it's dynamic equilibrium. Dynamic means that there's change involved, even though it doesn't look like any changes are occurring. And if you were to measure concentrations of substances in your reaction flask, they would stay the same, but that doesn't mean nothing's changing. Okay, and that's the important thing. There are no net changes, but the molecules themselves are constantly in motion and constantly interacting with one another. If you look at this little depiction of a reaction down here. We've got some molecules over here in panel A. Those are our reactants. You'll see in panel B some of our reactants have begun to form products. Over here in panel C we have some more products, and then in panel D we have what looks like no net change there. So when did this reaction reach equilibrium? The point at which the concentrations or numbers of particles of each type stops changing. So right around panel C is where we reached our maximum concentrations of both types of molecules. You'll see we have 3 of the double molecules and 4 of the single molecules, and over here in panel D we still have 3 and 4. So concentration hasn't changed, but what's implied by the drawing here is that the 2 molecules in panel C at the top have split, and the 2 in the middle in panel C have joined over here in panel D. And there's been another change sort of in the bottom row of molecules. So things are moving and changing, but the overall number of particles of each type doesn't change. It remains constant. Okay. So if we look at how the concentration of reactants and products change over time, we know from rate that things will start to the concentration of reactants will drop off, and the concentration of products will start to increase. Starts very low, concentration of 0, and moves its way up until you reach a point where the concentrations stop changing. In other words, the line flattens. Okay, and that's technically at equilibrium. But what we mean by equilibrium, the true definition of equilibrium, is that the forward reaction and the reverse reaction have the same rate. And so if you look reaction rate versus time, the forward rate, we know it starts fairly high initially, but as the number of particles of reactants decreases, so does the rate of reaction, so that starts to drop. The reverse reaction doesn't actually start to happen until you actually have some products that can turn back into reactants. And so you start at a very low rate, but as you start to form products, the reaction rate for the reverse reaction starts to pick up. And eventually you reach a point in time at which both rates are exactly the same. That's what equilibrium truly is. The forward rate of reaction is equal to the reverse rate of reaction. Okay? So the equilibrium position of a reaction is determined by some factors. First, the initial concentrations. Okay? The energy of reactants and products is going to be a factor here, whether or not the forward reaction is endothermic or exothermic, and vice versa. The degree of organization, in other words, are you becoming more ordered or less ordered as you go from one side of the reaction to the other? The overall goal is to reach a low energy situation and very high disorder. This is actually the second law of thermodynamics. That everything in the universe tends towards greater disorder, and greater disorder usually carries with it a lower energy. Okay, and we'll talk about that later on when we get to the second and third laws of thermodynamics. We refer to the equilibrium position as the reaction either lies to the left or lies to the right. If it lies to the left, what we mean is that there are more reactants present than products. In other words, the reactants don't seem to form very much product. And yet you can still be at equilibrium. It just means you've got a lot more on the left side of the reaction than on the right at equilibrium. If you were talking about lies to the right, it's the opposite situation. You have less reactants. In other words, more of the reactants form products, and you've got a lot on the product side. And yet the rate of product formation and reactant formation, the forward and reverse rate, are exactly the same. So a good analogy to think of this might be the belt line at rush hour. Okay, At rush hour, let's pretend for a minute that the speed limit is constant on both sides. It's both 55 miles an hour. So all the cars heading west are going 55, all the cars heading east are going 55. But the difference is at rush hour, you've got a lot more cars in the morning, you've got a lot more cars heading west than you do east. Even though the rate of speed might be the same, you have more cars going one way than you do the other, and vice versa on the way home, right? At the 5 o'clock hour, you've got a lot more cars on the eastbound side than on the westbound side, but they might be going the same. Let's pretend they're going the same rate of speed. That's what we mean by equilibrium lying to the left. Okay? If reactants are mixed, if you mix your reactants and nothing seems to happen, the concentrations don't seem to change, it means that the reaction could already be at equilibrium. That's a possibility. The rate of forward reaction might be so fast that it gets to equilibrium very quickly. Or it means that the rate is so slow that you can't really detect the change that's happening. And sometimes there are reactions whose rates are so slow that it takes a long time to get to equilibrium. So that's what we mean by equilibrium. We're going to use the terminology lies to the left or lies to the right fairly frequently. And you want to become familiar with what that means. Okay? In the next section, we'll take a look at mathematically what we can do with some of these things.